Okay, so good morning, everybody. Let's go ahead and get started. So our first speaker is from the University of Michigan, Anna Gilbert. She'll be talking about recovery of simple signals.
Thank you. I'm going to be talking about work in progress, and for a 25-minute talk, I really just want to give an advertisement for a model for a new way of looking at signal recovery problems. And so this is joint work with Brett Hemingway, Autry Rudra, Martin Strauss, and Mary Wooders is hiding behind a plant. Okay, so this is a cartoon of how I view a sparse signal recovery problem. You've got a signal or some population X, and it is of length n, it's very long, and you've got k important features in it. So for this cartoon, I'm going to be vague what I mean by important, what I mean by feature, and I'm going to be vague as to what I mean I'm not going to be vague as to what I mean by the matrix phi, but I'm going to be vague as to the specifications for phi. And basically, I've got a grossly underdetermined system, phi x equals y. There are m rows or m measurements or m tests that I am going to get from a linear fashion out of my unknown signal x. And I'm going to assume that there are k important things in x that I'm going to try and find. And so, broadly speaking, I think of a signal recovery problem as given phi and y, recover information about x. So I like to think about two important examples. One of them has been discussed tremendously, one of them not so much. So the first one that is natural and, quite old is known as combinatorial group testing. And this is slightly different from compressed sensing. So I'll go over this definition a little bit slowly because it's in some ways it's simpler, it's easier to understand, but it's quite different. So in this case, your vector x is a population of, say, healthy people or unhealthy people, and you can just think of this as a sparse binary vector. 1 signifies a defective item or an unhealthy person. 0 signifies acceptable or healthy. And you are going to acquire in a non-adaptive fashion measurements of this population with a binary matrix phi. So typically in group testing, this is called a pooling design. And I've put in red dots to signify that phi is sparse and binary. And your goal, upon given measurements y and the pooling design phi, your goal is to output the defective set in x. Not to try and recover, a good L1 approximation of x, but just who is unhealthy, which items are defective in x. And typically success is measured in terms of how many of the defective items you found, which is a way of saying it's not usually in terms of the L2 norm of various things. It's combinatorial, it's a count. Now, what's kind of interesting is that the arithmetic model, so how you carry out the multiplication phi times x is not done over the reals or the complexes. It's done with ORs, so Boolean arithmetic. Furthermore, it's not over Z2. It's Boolean. So a pool returns a 1 if there is a defective guy in that pool at all. It doesn't matter if there are 3 of them or 4 of them or just 1, returns a 1. And then if there are no defective guys in the pool, the measurement returns 0. So it's a slightly different model of arithmetic. Comparison with compressed sensing, this is much more familiar to everybody, so I don't need to belabor this very much except to say that how you determine the success of your output is measured in terms of the L2 error. So, and you ask for a good approximation to the original vector, and you ask that the L2 distance between the original vector be not that much bigger than the L2 norm of the tail of the vector. Okay, so I'm using all of this terminology to sort of implant in your in your mind what my definitions are. So if I sort the indices, if I sort the entries in X in decreasing magnitude, the tail consists of the n minus k smallest entries, and then the head are the k biggest ones. And so really what I'm asking is, how good is my output compared to the best k-term approximation to the original vector x? And here the arithmetic is done over R or C, so it's a natural model of arithmetic for analysts. Okay, so those are the two types of problems, the two setups for this to instantiate this cartoon of signal recovery. And now a lot of people spend time working on this design problem of designing both good matrices for signal recovery and good algorithms. Okay, so the goal is to design a good measurement matrix phi that has fewer than n rows. If you had n measurements, you could just take the identity and get the whole signal. And a recovery algorithm that is good in the L2 sense. So I'm really going to stick with the L2 errors here. So I measure the error of my output as compared to the L2 norm of the tail of the vector. Okay, and so there are two types of models, or two types of results for these design problems, two types of settings, if you will. There's the for all setting, or I'm going to implant the definition adversarial setting in your mind. And in this case, you would like to guarantee that your measurement matrix and your algorithm will recover all x. Okay, now typically with an L2 guarantee. Okay, so I'm really going to stick with the L2 norms here. So typically you insist that you recover all x's that satisfy a certain geometric constraint. Okay, and it is possible to solve this design problem for all signals with this L2 guarantee if you insist that the tail of x be really, really compressible. In other words, some sort of measure of the L1 norm of the tail as compared to the L2 norm of the tail. You can also ask, so for those of you who are really awake this morning, you can check that that square root k normally would be like square root n minus k if you knew nothing about the compressibility of the signal. And you can also plug in, if the L1 norm of the tail is bounded by this square root k times the L2 norm of the tail, you can plug this into the types of guarantees you get out of the work by Candes, Romberg, Tao, and Donahoe, and verify that, this is enough to get you an L2 error guarantee. But you have to be really awake. Okay, so other types of geometric constraints. You can ask that you recover all x that are block sparse or block compressible. You can constrain your sparsity patterns not to be any k-sparse signal, but or block sparse, but to be some connected chain in a binary tree, or more generally model sparse or model compressible. We heard a talk yesterday from Vulcan about all different kinds of models for which you could do this. So this is a very, very strong computational model. You could ask instead to recover for each x. So you could solve a weaker design problem. It's called this probabilistic or for each. And here you recover all x that satisfy some sort of statistical constraint, not a geometric one now, but a statistical one. And so one of them is you fix a signal. For any fixed x, I want to guarantee that I recover a good L2 approximation to x with high probability over my random construction of phi. So this is a probabilistic guarantee or a statistical model. You could also actually impose an honest-to-God distribution over all k-sparse signals, like some sort of random signal model. And we've seen examples. I guess it was on Tuesday. Guillermo's talk about random signal models. So there's been quite a bit of discussion of geometric models and statistical models. And so I want to argue that these models have pluses and minuses. I mean, the fact that we had much discussion about these should suggest that there's some pluses and minuses to each. In the adversarial case, you know, it's very strong, these results. You place almost no assumptions on your signal whatsoever. So it's widely applicable. Usually the argument is, well, I generate one matrix phi, I hard-code it into my hardware, I wheel around my 100-megapixel camera, and I'm good to go. Unfortunately, it's really hard to get these results. I mean, these are very strong mathematical statements, and it's very hard to get L2 guarantees in these very strong models. It's also, well, folks argue against computer scientists that worst case is unrealistic. You never see it. And then I would also argue, well, if you're going to impose geometric constraints, which geometric constraints should you impose? Should it be block sparse? Should it be connected in some chain, in some tree, etc.? So those are the pluses and minuses of the adversarial model. The probabilistic model has also its pluses and minuses. You know, from a mathematical perspective or a design perspective, it's much easier to come by positive results. If all you have to do is succeed with high probability over any fixed signal, you know, it's not that hard to prove things. It's not as applicable, right? I mean, you know, if I have to flip the little mirrors in my camera every time I want to take a picture, that kind of slows things down. It adds overhead to my architecture. And then, you know, the computer scientists are going to retort that it's debatable whether or not you can specify a really simple random process. You know, just like it's debatable whether or not nature follows worst case, it's debatable as to whether things actually are additive white Gaussians. You know, also you have to fully specify the random process. And furthermore, which random process? So, you know, there are pluses and minuses to these extremal models. So I promise not to make any political statements, but, you know, perhaps we should compromise. and perhaps we should acknowledge just what it is that we want to do with our systems. So there's always feedback in what we do. We never just measure, reconstruct once, and then go home. Okay? We are constantly measuring new signals, reconstructing them, measuring other ones. You know, so we're doing this in a sequential fashion. And you know, it's also sort of worthwhile to think that future signals that you're going to see are going to depend to some extent on the measurements of your current signals. So you could have benign dependency. For example, if you are keeping track in some compressed fashion of your store inventory, and you discover that you know, antihistamines are selling really well, and you go check, sure enough, the pollen count is really high. So you decide, well, maybe I should put the antihistamines up front and the Kleenexes up front, and I should put behind the sunscreen and the bug spray, you know, I should hide those in the back of the store. Then the inventory the next day or the next week is going to be some function of where you placed the inventory this past week. And you got that placement from reconstructing, you know, what sold really well. And so, you know, you've got it's a benign dependency, but there is some dependency. And you know, also there's adversarial dependency. Imagine that you've got some sort of compressed sensing radar detection system, and you detect an adversary is coming at you. You're going to take evasive action based on the signal reconstruction of these radar measurements. And your adversary is going to see your movements and then do something different. And you're going to measure again, and you're going to reconstruct. And so the adversary is going to get some sort of information about what you reconstructed just based on observing your movements. Okay? And so I want to emphasize that this is a different way of looking at adaptive measurements, where you take many measurements adaptively of one signal. And it's also different from I observe many signals simultaneously and take, you know, simultaneous measurements. It's really this notion of sort of a third acknowledgement of how we might use some of these compressed sensing or signal recovery systems. Okay, it's also interesting, a little plug for mathematics here. It's also interesting to look at the number of measurements that are required to achieve these types of error guarantees in these two different extremal models, because there's a huge gap, especially in the compressed sensing setting. And it would be really good to know what is in between these two extremals. And furthermore, can we figure out what is the minimum number of measurements required for these in-between models? So we've got the adversarial model on one axis and the oblivious or the probabilistic model on one side. And you can see, at least in the compressed sensing setting, if you insist on this L2 guarantee, you must take at least n measurements, some constant factor times n. And we know that in the oblivious case, you can get away with k log n over k. So it's a huge gap, an exponential gap. It's also really interesting to look at this for group testing. Group testing case, you need k squared log n over log k. In the adversarial case, and then in the oblivious case, something else. So there's actually, there are gaps in these two cases. And as a theoretician, I would like to investigate why are there these gaps, and what can we come up with that's in between these two models. Okay, so fortunately, we do have some examples of settings in which we have two extremal models, an adversarial model and a probabilistic model, and then models that are in between these two extremes for which you can get positive results. And so we were very much inspired by work from error-correcting codes. So I'm going to give a little side trip into these models for error-correcting codes. So at a gross level, you have a message M. You encode it. Let's say you encode it with an n-bit string. The alphabet here is 0, 1. You send it over a channel, and you get some received code word. And you can talk about the rate of the code book in terms of how many bits are in messages, divided by roughly how big the code book is. And so there are different models for what the channel will do to a code word. And there's an adversarial model, and there's a probabilistic model. And yay for Bell Labs. So they were promoted by two Bell Labs scientists. So there's the Shannon model, which is the oblivious or the probabilistic model, probably most familiar to statistical signal processing people. And this is the idea that the channel is oblivious to the message or the code word, doesn't care, and flips bits in the signal, independently from one another and independently from the message, changes zeros to ones, et cetera, with some probability. And then there's a Hamming model, which says, no. I want to do the worst case and code for the worst case. My adversary can change k bits, any k. My adversary could be factoring absolutely gigantic numbers and have all kinds of computational power change k bits. And so this imposes incredibly strict conditions on your code book. And you actually get quite a gap in terms of the rate for codes in how many fractions of errors, what fraction of errors these two different models can correct. So there's a big gap between adversarial and probabilistic in coding theory, and there's a middle ground. I've got pictures of not Bell Labs people. Who did quite a bit of work, actually quite recently, on this middle ground. And they say, no, my adversary is going to change at most k bits, but my adversary has some limited power. So I'm going to restrict the computation or the information that my adversary can glean about the code word. And so the types of restrictions that you might want to place on your adversary would be, my adversary can run algorithms only in probabilistic polynomial time. So this is a totally practical limitation to impose on my adversary. I'm not going to give my adversary enough power to factor. This is totally reasonable. And it's not an actual limitation in practice. Or, I could have an adversary that has very small memory. So just like log space to do any sort of computation in which to figure out which bits to flip, to change. Okay, and so very recently, Guruswamy and Smith were able to construct very high rate code books against these types of bounded adversaries, so that these are meaningful models and sort of split the difference between the extremals in coding theory. So we want to do the same. So we want to come up with the right sort of computationally bounded adversaries for signal recovery. So we're going to imagine that we're playing a game. We get to design a matrix phi and a recovery algorithm, and we're playing a game against Mallory, who is a malicious adversary. And sometimes Mallory has limited power and sometimes she doesn't. I guess Mallory is maybe the dummy that the Kung Fu Panda is playing against. There are a couple of different interesting models. The first one is most interesting for group testing. It's just essentially Shannon's model, the binary symmetric channel. We're gonna have items be defective with a certain probability, or not defective with a certain probability, completely oblivious to zero mutual information with whatever sort of measurement matrix we construct. So oblivious there. Mallory generates our signal with absolutely no information about phi. And then, then we've got sort of a couple of intermediary models in between oblivious or probabilistic and adversarial. So one of them, I'm just going to highlight one of them. Suppose Mallory gets to see this measurement matrix phi. But Mallory can see it in sort of a limited fashion. She can read phi, but all she can do is stream over the rows of phi, see entries in the rows of phi, and she has a very small amount of space. So she does not have enough space to store all of phi, but maybe she could store an index of an interesting column. Right? Maybe she could store some sort of stuff. And then she's going to use that information to produce a vector x, and we have to take that vector x, our matrix phi, and our recovery algorithm, and try and get a good approximation to the measured vector x. Okay, so these are models directly inspired by bounded adversaries for error-correcting codes. Okay, so I apologize to the theoreticians in the audience, all three of you. And let me give a short little example of what do I mean by an adversary up against a randomized algorithm. What does that mean? Okay, so here's a really simple example. My input strings, they're of length n, and let's say half of them are A's and half of them are B's. And I want to design a randomized algorithm that will produce or return the position of A, some A, in this vector. Okay, so my algorithm is going to pick k positions out of n at random, and it's going to check these k positions. And if A is in at least one of these, that should be m positions at random. If A is in at least one of these m positions, return the position. You succeed, right? The algorithm succeeds. And if you don't see an A, you should return the empty set, and the algorithm fails. Okay, so this is a randomized algorithm that takes an input string and a random string, a string of random positions, and it has some failure probability or some probability of success. You can quickly verify what the probability is. Now, it's important that this is on any fixed string. If my adversary knows where my positions are, if my adversary knows what my random string is, all Mallory has to do is put B's in those positions that I'm going to check, and the algorithm is guaranteed to fail. Okay, now, what if Mallory doesn't know all m positions, but what if Mallory only knows log m of those positions, or m over 2 of those positions? If Mallory has limited information, I can still come up with, I can still run this algorithm and succeed. I'm not going to succeed with as high probability anymore, but I'm still going to succeed. Okay, so this is what I mean by a randomized algorithm, by an adversary with a certain amount of information, and what I mean by succeed or fail, and also an instantiation of this sort of game that one would play against Mallory. Okay, so you can cast the group testing and sparse recovery as problems just like this finding the position of A. In fact, finding the position of A is sneakily close to a signal recovery problem. And you can look at the number of measurements that are required in all of these different computational models, or all of these models for your adversary. So we've got combinatorial group testing as the first chunk, and compressed sensing is the second chunk. There are known results for some of these different models, and I've put the appropriate references in there. And then all of the references that say new are an advertisement for the things that we've done. You can actually see some interesting differences between group testing and sparse recovery. So, in a previous life, I was a mathematician. I think it says something interesting about what models of arithmetic what is the difference between Boolean arithmetic and arithmetic over a field of characteristic 0? So you get all these different gaps in the numbers of measurements. So for the sake of time, I'm just going to give you one slide as to why these results work, or how they work in the case of compressed sensing. And one of them is to look very much at what is the geometry of the null space of a random matrix phi, what is the geometry of the null space of phi if I fatten it up by certain geometric constraints. And then against the information theoretic bounded adversary, we use a simple lemma that has to do with randomized algorithms against adversaries, and then streaming adversaries, a communication complexity argument. This is really an advertisement for the paper and the work in progress, no technical content. Okay, and I'm going to end by saying that in many ways, we actually have a good story for compressed sensing because, against all of these adversaries, you only need the same number of measurements that you would need against an oblivious, really weak adversary, and you still get L2 guarantees. For group testing, it's actually more interesting. These adversaries are more meaningful. You get different numbers of measurements. And so this model, we think, seems to be a good compromise between two extremal positions, and a computational alternative to statistical or geometric models. And also, I think, a recognition of this measure and reconstruct feedback loop as opposed to adaptive measurements and as opposed to simultaneous measurements. Okay, thank you.
So are there any questions? No questions?
Okay, good.
No?
No, that's fine.
Okay, so thank you, Anna. So you were a mathematician in your previous life?